So here's an integral that we want to try to tackle, and as always we need to try and decide what the best technique of integration to apply to this particular integrand is going to be. Doesn't really seem like a u substitution is going to be successful. Like if we tried to let u equal this denominator, I don't think we're going to get the right cancellation to occur with what I see up in this numerator, so that doesn't really seem like a good bet. I do notice that we have a denominator that could potentially factor. And so what I'm going to go ahead and try to do is I'm going to see if we can factor this denominator and then try to break this up into the sum of two separate fractions. So basically I'm going to try to do a partial fraction decomposition here. So the denominator, if I factor it to x and x in those positions and minus 1 and plus 2 in those positions, outer times outer gives me 4x, inner times inner gives me minus 1x. There's the plus 3x I need, and we have this thing factored. Now I chose this particular integral for the review sheet for chapter 6 without realizing what I could do at this point. At this point, check out what you have going on. You have a factor of 2x minus 1 in the top, a factor of 2x minus 1 in the bottom. Since this is written as multiplication, you can go ahead and cancel these and rewrite this as 1 over x plus 2. Let's say you didn't even realize that. Let's say you went ahead and proceeded with the partial fraction decomposition. You're going to assume that this can be rewritten as some value a over 2x minus 1 plus some other constant value b over the second linear factor, x plus 2. Now if you were going to add these two fractions together, you'd have to have a common denominator, and you'd have to multiply this denominator here by x plus 2, and so you'd have to multiply this numerator by x plus 2, and so that'll give you a times x plus 2 over 2x minus 1 times x plus 2. And then we'd have to take this second fraction and we'd have to multiply its denominator by 2x minus 1 to create the common one. So we're going to have x plus 2 times 2x minus 1, but I'm also going to have to multiply that numerator by that same exact value, right? We have to multiply by some form of the number 1. So now if we do a couple of distributions here, if I distribute into this numerator, I'm looking at ax plus 2a, and if I distribute over here, I'm looking at plus 2bx and then minus b. Since I have a common denominator, I can write everything as a single fraction now. So I have the numerator in simplified form over this common denominator. Now at this point, we know that this fraction is still equal to this fraction. So 2x minus 1 over 2x minus 1 times x plus 2, these have to be equal to each other. If I multiply both sides by this denominator, the denominators basically cancel. So this numerator has to equal this numerator. In order to carry out this partial fraction decomposition successfully, what we're going to have to do is we're going to have to turn this one equation into a system of equations. And what we can use in order to do that are coefficients. The coefficient of x right here is 2. The coefficients of my x's over here, the a and the 2b, those are going to have to combine to 2. So 2 is going to be equal to a plus 2b. Right, the coefficients of the x's on the right side of this equation have to combine to the coefficient of x on the other side. And then the constant terms on this side, 2a minus b, those are going to have to combine to the constant term on this side, which is negative 1. So negative 1 is going to have to equal 2a minus b. Now you have a system of equations, and you want to solve this system for both a and b. I'm going to use substitution to solve this. It's easy to solve this for a. So I'm going to subtract 2b from both sides, and a is going to be equal to 2 minus 2b. If I substitute that in place of my a on the other side, I'm looking at 2 minus 2b in place of the a minus b. It's just some algebra at this point. So we'll go ahead and distribute in. That'll give us 4 minus 4b minus b. I'm going to subtract 4 from this side. So that'll give me a minus 5. And then these are like terms. I have minus 4b minus 1 more b. There's minus 5b. Divide both sides by negative 5, and I get that b is going to have to equal 1. Well, if b equals 1, what's a going to equal? Well, 2 minus 2 times 1 is what a is going to equal, and that's going to give us 0. So a is going to equal 0. So if we go back to what I said earlier, And I said I didn't anticipate this happening. This doesn't regularly happen when you do a partial fraction decomposition. We could have gotten to this result much more quickly than the way that I just went about this. I could have canceled this with this and gotten 1 over x plus 2. If I put 0 in place of my a, that's the value we got for a, and I put 1 in place of my b, I get the 1 over x plus 2 a lot more quickly. So the original integral, through either a partial fraction decomposition like I attempted to carry out here, or through simplification, you're going to end up with the antiderivative of 1 over x plus 2 with respect to x that you're going to try to carry out. You would have to do a little u substitution in order to allow this integral to be done. So the derivative du dx is going to be equal to 1, so therefore du is going to be equal to dx. So this integral is going to be equivalent to the integral of 1 over u with respect to u, which gives us natural log of the absolute value of u. It is an antiderivative. We'll tack on our plus c. We want to back substitute, and we're going to get x plus 2 back in place of the u. So here is the antiderivative of what we started with. I definitely did this the long way, but I did want to show an example with a partial fraction decomposition. Anytime you're looking at an integral that looks like this, a denominator that factors to two distinct linear factors, two different linear factors, a partial fraction decomposition, although a little lengthy, shouldn't be too difficult in order to carry out.